Yes, we've been talking about polynomial inequalities all this while. I mean, I think in the last 4 or 5 videos or so, been talking about polynomial inequalities. So I suspect this will be the last video on inequalities as far as this playlist is concerned. Of course, we still have other things to discuss as far as polynomial equations are concerned. So applications of polynomial inequalities. So we've seen the concept of inequalities. We've also seen the how to actually find how to describe polynomial inequalities using the sign chart method. Yeah. Then we went ahead to see um how to solve inequalities. That was in the last video. And now since we now have all of these things in our kitty, we want to go ahead and see some of the real life applications of polynomial inequalities. So um here now we see that polynomial inequalities of the form P of x greater than or equal to 0, P of x greater than 0, P of x less than or equal to 0, and of course P of x less than 0 arise naturally when we model real world constraints. So and we have typical variable meanings like t for time. So we can have inequalities in time, inequalities in describing length, distance, and position, price of quantities or commodity, Q quantity produced or sold in economics. So or commerce, the solution set often one or more intervals tells us when or for which value is a certain condition, e.g., height, which is not negative, or profit, which is positive, holds in context. So in this case, in as much as we can get all mathematical solutions of whatever we are describing, we need to pay attention to the fact that not the idea of non-positivity holds when we are thinking of things like time, length, price, and quantity. So, from real world statements to polynomial inequalities, we have some general steps. So, first of all, you need to define whatever variable you're dealing with, define the variable clearly and attach the units. Example, let t be the time in seconds after an object is thrown. Time in seconds is very important. Write a polynomial expression that models the quantity of interest. So, an example will be height of an object will now be h. The height as a subject as a function of the time is now given as minus 5t squared plus 20t plus 10. Then you can translate the verbal condition into an inequality. For instance, you want a non-negative height. So in this case, now you want this polynomial to be greater than or equal to 0 because height should not be negative, right? Height can be 0, like if there's no movement. Then profit is positive, so P of Q is greater than 0. So now you see real life situations leading to inequalities like that. Then you can then go ahead and solve the polynomial inequality algebraically by factoring, by using sign charts, and by graphing, and so on. You can then interpret the solution intervals in the original context, where you now attach units, decide whether endpoints are included, check if any extraneous values are violate natural domain, e.g., negative time. So if you have two solutions, one gives you negative time and the other is positive time, of course, you should do away with the negative time because time is not negative. Okay, so let's look at physical constraints, like non-negativity of height, distance, and area. So physical quantities like height, distance, area, volume, and mass cannot be negative. So this gives inequalities of the form height, h of t greater than or equal to 0, distance from origin, d of t greater than or equal to 0, area is a of x greater than or equal to 0. An example is area of a rectangle. Imagine that the length is fixed. The length of a rectangle is fixed at 10 cm and the width is x minus 2 cm. And then the question, so the area, of course, automatically will be a of x, which is 10 times x minus 2. So, and you have this physical requirement that the area must be greater than or equal to 0. Okay, and the width is x minus 2 itself has also got to be greater than or equal to 0. So in that case, so 10 into x minus 2 greater than or equal to 0 simply implies that x minus 2 is greater than or equal to 0. That means that for this to happen, you need values of x that are always greater than or equal to 2. If not, so of course, the worst case you should have is when x is 2 and everything goes to 0, or but you can't have x is 1, for instance, because 1 minus 2 will be minus 1 and the area will be negative. That is not allowed. So x greater than or equal to 2 means at least this least value of x you should have is 2. Next, it will be 3 so that you can have at 0 and positive values. So interpretation, the parameter x must be at least 2 cm for the rectangle to exist with non-negative width and area. Okay. Then we go ahead and talk about the height of a projectile, like time interval above ground. So let the height in meters of a ball be modeled by h of t equals minus 5t squared plus 20t plus 15, where t is time in seconds after it is thrown. So the physical constraint here is that a projectile cannot go below the ground. So we require that h of t is always greater than or equal to 0. Now we can solve the inequality, you know, so we say minus 5t squared plus 20t plus 15 is greater than or equal to 0. That's the description of the height from the formula. Then the step one there is to set the quadratic equal to 0. First of all, I mean, that was what we learned in solving inequalities or in describing polynomial inequalities. Solve the polynomial equation first of all and get the roots, and from there you can do other things you need to do. So, having set this to 0, you can divide through by minus 5. So at the end of the day, you can have t squared minus 40 minus 3 equals 0. And you can solve using the quadratic formula. So here now the a is 1 because the coefficient of t squared is 1. B is minus 4 and c is minus 3. So you have the discriminant b squared minus 4ac. That's minus 4 squared minus 4 times 1 times minus 3. That is 16 plus 12, which is 28. That means you're going to have real roots, two distinct real roots. So, and the root formula will now be t equals 4 plus or minus root 28 all over 2. That's 2 plus or minus root 7 because root 28 is 4 times 7. Root 4 is 2. So you have 2 root 7. And then, 4 divided by 2 is 2. Then 2 root 7 over 2, you have this left. So thus, we can say that the intersection times are t1, which is 2 minus root 7, and t2, which is 2 plus root 7. Now, if you do the approximations now, root 7 is something like 2 point something. So it means clearly t1 is negative. So t1 is approximately minus 0.6458, while t2 is 4.6458. Okay. So the interpretation now is this. Since the parabola opens downward, the height is non-negative between the roots. So t belongs to is somewhere from in the closed interval t1 to t2, but only non-negative time makes physical sense. So we have to discard t1, which is negative. There's nothing like negative time. So only t2 is admissible in this situation. So we can say the ball is on or above the ground for t between. So because this is negative, we can get rid of it. So and just bound and have this positive boundary 0, 2 plus root 7. Though mathematically speaking, we have a negative result, but we don't need that because it's not admissible when you talk about time. So at the end of the day, we have your time from 0 to 4.65 seconds. So that makes sense in that case. So we can also talk about geometric and distance constraints. Of course, polynomial inequalities naturally arise in geometric, spatial, and motion-related problems. In many real-world systems, a polynomial represents a distance, length, radius, height, or displacement, and physical constraints require these quantities to stay within safe or allowable bounds. Solving the associated inequalities reveals when the system operates safely or feasibly. So these polynomial inequalities help us to set necessary boundaries that'll make whatever situation we are considering make actual sense. So first of all, we have common geometric and physical constraints, like we have radial or safety zone constraints. Many machine, robots, or rotating systems require objects to remain within a safe radius. All right. So distance from center can be something like r of t. Maximum safe radius is r max. So the constraint can now be that the distance from the center should be at least less than or equal to the maximum safe radius. So if r of t is a polynomial, then this becomes a polynomial inequality. So you see how we can make a physical phenomenon into a polynomial inequality. So then another thing, apart from radial or safety constraint, we can also have something like length or thermal expansion constraints. So materials expand or contract according to temperature, often modeled by a polynomial. So when a body is heated, right, there's a tendency for it to expand. When it is cooled, there's a tendency for it to contract. All right. So we can first of all see, so we can model that kind of thing like this, that we can look at length as a function of temperature, so L of T. So we can then have allowed operating range, that the minimum length is less than or equal to the length of, so whatever length we are talking about, the length of as a function of temperature lies between the minimum length and the maximum length. And then apart from length or thermal expansion constraint, we can talk about distance between moving objects. So to avoid collision, right, you have cars moving and everything. Like in the design of uh, in the design of robot in these days when we have electric cars and self-driving autonomous vehicles and all of those things, we need to pay attention to these kind of ideas that talking about distance between objects, collision avoidance or tracking models often require that d dt is greater than or equal to d naught, ensuring objects remain at least d naught units apart, right? When d of t is a polynomial, this is again a polynomial inequality, okay? So you want to avoid collision. You want to be sure that the distance between objects is at least greater than or equal to a baseline distance to avoid a possibility of collision. So let's look at a worked example involving safe distance for a moving car. Imagine that a car's distance from a barrier is modeled by d of t equals t squared minus 8t plus 15. All right. And the safety requirement must be at least 2 meters away. Right. So the closest barrier to it should be at least 2 meters away. So in that case, now we want to be sure that d of t is greater than or equal to 2. Now here we have t squared minus 80 plus 15 greater than or equal to 2. So we can then form the inequality to say t squared minus 80 plus 15 is greater than or equal to 2. And we can move all terms to one side so that we have t squared minus 8t plus 13 greater than or equal to 0. And of course, whenever we are dealing with polynomial expressions like polynomial inequalities like this, the first thing to do is to solve the problem as if there's no inequality. So we solve the quadratic, which is t squared minus 80 plus 13 equals 0. And first, we can get the discriminant to know if there are real or imaginary solutions. So the discriminant is b squared, which is minus 8 squared. So minus 8 squared minus 4ac. 4 times 1 times 13, that's 52. 64 minus 52 is 12. So since it is greater than 0, then it means we are going to have two distinct real roots. So we have these roots now. T is 8 plus or that's plus or minus b. That's sorry, that is minus b. That's minus a. That's 8 plus or minus square root of uh you know b squared minus 4ac, which we have found to be the discriminant 12 all over 2. So this is 8 plus or minus 12 is 4 times 3. So you can then say 2 root 3. So 8 over 2 is 4. 2 root 3 over 2 is root 3. So you have the approximate values now to be 4 minus root 3 and 4 plus root 3. 4 minus root 3 is approximately 2.27, and 4 plus root 3 is approximately 5.73. Okay, so we can then determine where the quadratic is non-negative. So since the parabola opens upward, right, it is positive outside the roots and then negative between the roots. So in that case, now if you then say t if you have t less than or equal to 4 minus root 3 or t greater than or equal to 4 plus root 3, so we said already that since the parabola opens upwards, right, the original expression we have, right, is the distance uh modeled, right, and it goes like in the form of a parabola. So in this case now, we say it is positive outside the roots. So we have these two roots now. So see that less than the small one, or less than or equal to the small one, or bigger than or greater than, greater than or equal to the big one. So we have t less than or equal to 4 minus root 3, or t greater than or equal to 4 plus root 3, because with that, we need to avoid the barriers. So anything greater than 4 minus root 3 is going to be a problem. Anything less than 4 plus root 3 is also going to be a problem. So the interpretation here is that the interpretation here now is that the car remains at least 2 meters away from the barrier for t less than or equal to 4 minus root 3 or t greater than or equal to 4 plus root 3. This is now like an OR inequality. This means that at the beginning, the car is safely distant when it starts out. Then it enters the danger zone for some time. After passing that interval, it becomes safe again. All right. So we have that. So the general interpretation in this case is that for any geometric or motion-based constraints, the solution intervals indicate when the system is safe, feasible, or within design limits. Okay. Then you have polynomial. Okay, well, we can even do this. We can do this plotting here to even understand what is really happening. T squared minus 8t. Okay, this is what we are solving now. T squared minus 8t plus 13. Okay, let me go for decimals now. Before I go too far, t squared minus 8t plus 13. So, we have to use x squared, all right, minus 8x plus 13. Okay, I think I can even use t squared. Yeah, let's not be too closed-minded. T squared, okay, it's not working, right? Plus 8t, minus what was that again? T squared minus 8t plus 13. Okay, t squared minus 8t plus 13. Okay, okay, this is not working. So we have to go for x. So x is the go-to thing. Yeah. So you see this now. So this is what we have. So you see now that since we want only the positive side of things now, so you see that has to be. So you can see it has to be like we have to have x. Aha, this expression here. So this expression is 2.26975. Or so this is that expression now. This what is it now? 4 minus root 3, 4 plus root 3. So this is 4 minus root 3, and this is 4 plus root 3. So it means we need to have, so for it to be positive, you see the negative is between, so within this range, it's negative. So you see the positive sides are all only up here. So we have x less than 4 minus square roots of 7. Oh, square root of 3, not square root of 7. Square root of 3. So you see that. And then we have this now. Then we now have, okay, so that's less than or equal to, by the way. And then we have this now. 4 is greater than or equal to 4 plus root 3. So you see here now, this is the negative side. So this function is only positive within this range. And that is why, so the car is only safe. It's not safe in this range at all. So while if the car is in this range, it means it is in danger zone and it shouldn't be there for too long. Okay. So determine the quadratic is non-negative. We've determined that already, from the plot. And of course, we also have the sign change method to do the sign change chart, I think. So the interpretation now is the car remains at least 2 meters away from the barrier for 4 minus root 3 or t greater than or equal to 4 plus root 3. This means at the beginning, the car is safely distant. It enters the danger zone for some time. After passing the interval, it becomes safe again. So while the car is within this range, it is in danger zone, and then it goes to safe zone later on. Okay. So we have the general interpretation now that for any geometric or motion-based constraint, the solution intervals indicate when the system is safe, feasible, or within design limits. Polynomial models approximate motion trajectories, mechanical deformation, oscillations, radial distances, heat-induced expansion. Thus, polynomial inequalities are crucial for safety analysis, engineering design, and system monitoring. Okay, so we see the usefulness of polynomial inequalities. Now we have that economic applications of polynomial inequalities can also be done in this sphere. So here we're talking about revenue, cost, and profit, for instance. So imagine core economic functions, often polynomial in terms of Q, that's quantity of goods produced. So imagine you have a revenue function. Revenue measures total income from selling Q units. And the general form can be something like R of Q. Oh, that's long. Okay. You have R of Q equals P over Q multiplied by Q. So if price is constant, say P is constant, then you can say that R of Q is P times Q, a linear function in terms of Q. So if price depends on quantity, for example, demand increases as Q increases, then P of Q may be polynomial, making R of Q a polynomial as well. Okay. And then so that's the revenue function. So imagine you have revenue function to be R of Q. And then the cost function can also be modeled like that. So the cost measures the total expense of producing the Q units. So denoted by C of Q. So we have common polynomial forms. The cost function can be linear. So we can have linear cost, which is C of Q equals AQ plus B. You can have quadratic cost function, that's C of Q equals AQ squared plus BQ plus C. And then we can have higher degree polynomials, which can model more complex cost behaviors, e.g. increasing marginal costs. Okay. Then from that, we can then have a profit function. So we can have profits. Profit is revenue minus cost, as we know already. So profit, P of Q, profit as a function of quantity is equal to revenue as a function of quantity minus cost as a function of quantity. So if R of Q and C of Q are polynomials in Q, then we can say P of Q is also a polynomial in Q. So studying when a business makes profit or loss becomes a problem of solving inequalities like P of Q is greater than 0. That's the profit must be greater than or equal to 0. Then for break-even analysis, right, we have P of Q is 0. So to make profit, you have P of Q is 0. Then loss becomes a problem. Okay, yeah, P of Q is 0. P of Q greater than 0. That's profit, good profit. P of Q is 0. That means there's no profit at all. Maybe you just break even. Then P of Q less than zero. That means a kind of loss there. So profit, break even point, and loss like that. So when profit is greater than zero, that means uh that's profit, like that's actual profit. P of Q equals zero, that's break-even point, and P of Q less than zero, that is actually doing business at a loss. Then we can then have profit-based inequality conditions. So we can break even, for instance, just like I said, break even occurs when profit is zero. So P of Q is zero. At break even, revenue equals cost. Because if you look at this expression now, since we said profit is zero, so that means R of Q minus C of Q is zero. That means that the revenue is equal to cost at that point. So economically, the firm neither makes a profit nor a loss. At least it's better than losing, right? But it's worse than making a profit, but at least it's fair. So profit occurs when P of Q is greater than zero. This means R of Q is greater than C of Q. So the corresponding values of Q, which is quantities produced, are profitable production levels. So anytime you make profit, it means that you have the value of Q at that point is what you need to produce to make profit. Okay. Then we can also have loss, right? For loss, loss occurs when the profit is less than zero. P of Q is less than zero. This means R of Q. That means the revenue is less than cost. So you spend more in producing than what you make. So the corresponding values of Q here are unprofitable production levels. So imagine a worked example where we have given function. Suppose revenue R of Q is 50Q and the cost C of Q is Q squared plus 20Q plus 100. The profit function will simply be P of Q equals R of Q minus C of Q, that which is simply 50Q minus Q squared plus 20Q plus 100. So you can expand all of that. You have 50Q minus Q squared minus 20Q minus 100. So 50Q minus 20Q can go. So you have 30Q here. So minus Q plus 30Q minus 100. Okay. So in this case, now you can then estimate the profit, look at the profit, the loss, and break even. So P of Q now is equal to minus Q squared plus 30Q minus 100. This is now the profit function we have. So this is a quadratic polynomial that opens downward because the coefficient of Q squared is minus 1. So you see, it opens downward because this coefficient, I mean, we've learned a lot about the leading coefficient and the degree, right? So to now deal with the profit in proper terms, I think something is not proper here. Let me see what that is about. Let's see. I think it's a long way off. Yeah, so I need to use dollar signs here. Dollar, 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 dollar. Yeah, I think that works. So back at the story. So yeah, here now. So profit condition as a polynomial inequality. So to find when the business makes profit, then we need to solve P of Q greater than zero. So that's minus Q squared plus 30Q minus 100, which is greater than zero. If we multiply by minus one, so we have Q squared minus 30Q plus 100. Of course, this greater than has to become less than zero. So Q squared minus 30Q plus 100 is less than zero. Now we solve the quadratic equation, Q squared minus 30Q plus 100 equals zero. So you solve that first to get the solutions to the polynomial equation, and then you can then look at the inequality. So using the quadratic formula, we know Q is minus B, that's minus 30, which is 30 plus or minus square root of B squared, that's 30 squared minus 4 times 1 times 100, that's 4AC. So that's 30 plus or minus square root of 900 minus 400 over 2. That's 30 plus or minus root 500 over 2. I mean, root 500 is root 100 times 5. That's 10 root 5. We get now 30 plus or minus 10 root 5. So 2 goes in 30 15 times, 2 goes in 10 5 times. So we have 15 plus or minus 5 root 5. So the roots will now be Q1, 15 minus 5 root 5, Q2, 15 plus 5 root 5. Now, because the quadratic Q squared minus 30Q plus 100 opens upward, it is so because it opens upward, right? So we are going to have two parts, just like what we had previously. So it means we are going to have that Q, so both okay, negative between the roots, positive outside the roots. Okay, let's even try to plot it. Q squared minus 30Q plus 100. Okay, we know we have to use X, right? Because X squared minus 30X plus 100. X squared minus 30X plus 100. Okay, so this is what we have. So here now you see that the positive parts are in all these places now. So what are we even analyzing? We're analyzing profit. So because the quadratic q squared minus 30q plus 100 opens upward, it is negative between the roots. Okay. So you see this between this root now, we have negative, right? And then positive outside the roots. That means that this before this point, up like this positive, then after this point positive, but in between it is negative. So we don't want that portion. Therefore, the inequality q squared minus 30q plus 100 less than 0 is satisfied when you are inside, you are within the roots. That's 15 minus 5 roots 5 less than q less than 15 plus 5 root 5. So that is if you want if you are talking about loss, right? Does the profit equation P of Q has got to be greater than 0? In that case, now that means Q is an element of this. So how did okay, yeah, this is what we are trying to satisfy now. So for profit, actually based on the problem itself, right? We want this to be less than 0. So we want the negative part here, interestingly. So in that case, for that profit to be satisfied, because that's the polynomial we're trying to solve, so it means that we need that negative part. So that's like Q falling between 15 minus 5 root 5, 15 plus 5 root 5. In short, this is what we have. So we have 15 minus 5 square roots of 5 is less than x, and that is also less than this whole thing now, this whole thing, where we change the sign to plus. So in between now we have plus. So you can see, if you take this home now, okay, that's so large, so we need to shrink it to see. So it means that the profit only happens within this interval based on this is what we're solving, right? So we need the negative part of that polynomial for the profit to be possible. So you can only get profits when the quantity produced, I think we got this is Q we have got now. Okay. Where is it? Okay, so this represents the range of quantity Q for which the business makes a positive profit. So it means you have to sell between 15 points. In fact, we can try to evaluate 15 minus, let's try to evaluate 15 minus this. I'll just put it here. So yeah, so 3.819, and then here, if you put plus, so you need to sell between anything from 3 to 26 items. Maybe you are selling exotic cars or whatever you're selling. You need to sell minimum of 3 and maximum of 26 to make profit. If you sell below that, below 3.81, you're going to suffer loss. If you sell above 26, you're going to suffer loss. So anything from 3 to 26 is what you should sell to make profit. Okay. So let's talk about the economic interpretation of the solution interval. So the range of profitable production now, the interval Q1, Q2 is 15 minus 5 root 2, 5 root 5, comma 5 plus 15 plus 5 root 5. Represent the range of quantities Q for which the business makes a positive profit. With this interval, P of Q will be greater than 0 here, and the revenue will be greater than the cost, which is what we want, and production is economically worthwhile under this model. Then loss for too little or too much production. So if we produce too little is below 3.81, too much is above 26. So there can be a loss. So loss for too little or too much production. If Q is less than 15 minus 5 root 5, production is too low to cover fixed and variable costs. So in this case now, the profit is less than 0, so the firm operates at a loss. If Q is greater than 15 plus 5 root 5, production is too high and rising marginal cost outweigh revenue. So P of Q will be less than 0 also again. So this is loss due to overproduction. So there can be overproduction leading to loss, and there can be less production, too low production, which leads to loss also. So both underproduction and overproduction can lead to loss. So you need to get, and that's why if you're into business or something, you have to go mathematical, so you can actually have clear idea of what you should be doing, so that you don't just operate work aimlessly. That is. So talking about graph and shape interpretation, I think I've plotted the graph and I've even demonstrated it as much as possible. So P of Q is minus Q squared plus 30Q minus 100 is a downward opening parabola. So the Q axis intercepts occur at these 2 points. So between these intercepts, the graph lies above the Q axis. So you have P of Q greater than 0 for profit. Then outside this intercept, the graph lies below the Q axis. So you have P of Q less than 0. That leads to loss, since that is what we want. So, in summary, revenue, cost, and profit functions in economics are often modeled using polynomials in the quantity produced Q. The sign of the profit uh, function P of Q determines whether the firm is in profit, that's P of Q greater than 0, or whether the break even, that's P of Q equals 0, and loss, P of Q is less than 0. Okay, so determining these regions is equivalent to solving polynomial inequalities. Now, if you want to look at the break-even point, the break-even point at this actual point, this actual 15 minus 5 root 5 and 15.5 root 5, those are the actual break-even points. So if they produce those amounts, so it means if the production is 3.81 or 26.18, then the company breaks even. But if you produce in between those values, yeah, you make profit. If you produce less than or above, less than the lower and above the higher, that's a loss right there. So loss is P of Q less than 0. So determining these regions is equivalent to solving polynomial inequalities. So the solution intervals have clear economic interpretation. They tell us which production levels are profitable and which lead to loss. So we talk about economic applications. We have price intervals and feasibility. So another economic application. So what we did the other time is about production and everything. So what about talking about price intervals and feasibility? It's about the same idea. So polynomial inequalities appear naturally in economics, especially when modeling demand, revenue, cost, and profit as functions of price. Okay. So the other time we talked about production, revenue as function of quantity produced, and profit as function cost as function of quantity produced, such that the profit is now revenue minus cost, and everything is a function of quantity produced, which we're able to find. So solving these inequalities helps identify feasible price ranges, profit making intervals, and economically meaningful regions of a model. So number one, polynomial demand and price constraints. Demand as a polynomial, for instance, a price demand relationship is often modeled by a function. That is, you have the demand function, D of P, which is quantity demanded at price P. And you have typical examples like you can have linear demand like D of P is A minus BP, quadratic demand D of P, that's A minus BP minus CP squared. And then you can also have higher degree polynomials for more complex behavior. But these ones are more common. So because D of P represents a quantity, it must satisfy non-negativity constraint. That is, demand has got to be greater than or equal to 0. Because if demand is less than 0, it makes no sense. So if D of P is less than 0 for some price P, that part of the model is not economically meaningful, and such prices must be excluded. So you don't need that at all. So then we have profit positivity as a polynomial constraint. So for profit function, our profit is usually defined as P of P. That's profit as a function of price is now revenue as a function of price minus cost as a function of price. And revenue can then be seen as revenue as a function of price equals the price times uh, demand, right? Demand as a function of price. So the cost now is cost of P is often modeled as a polynomial, e.g., included fixed and variable costs. All right. So if G of P is a polynomial, then R of P is typically a polynomial. So P of P becomes polynomial also, or at least an algebraic function of P. So then we can have profit feasibility. So a common economic requirement would be that we have positive profit, that is P of P is greater than 0. Thus, we often end up solving two inequalities. So you solve the demand, which is non-negative, D of P is greater than or equal to 0, and the profit, which is P of P, which is greater than or equal to 0. So each inequality uses an interval or union of intervals or admissible prices. The economically feasible price range is the intersection of these intervals. And that is why we have demand and supply curve, right? So we have a worked example here, non-negative demand. Suppose the demand function is D of P equals 100 minus 5P minus P squared, where P is the price in dollars, and D of P is the quantity demanded in units like that. Okay, so we have the non-negativity condition. We require that D of P is greater than or equal to 0 implies that 100 minus, which implies, right, that this is greater than or equal to 0. So you have 100 minus 5P minus P squared greater than or equal to 0. So we have to rewrite in standard form like we learned in previous videos. So we write a standard polynomial form. So you have minus P squared minus 5P plus 100 greater than or equal to 0. So multiply both sides by minus 1 So this reverses the inequality. So you now have p squared plus 5p minus 100 less than or equal to 0. Then you can solve the quadratic inequality. So first solve the quadratic equation, p squared plus 5p minus 100 equals 0. And then you can use the quadratic formula. So using the quadratic formula, you have minus b. A is 1, b is 5, c is minus 100. So minus b, that's minus 5 plus or minus square root of b squared, that's 5 squared minus 4 times a times c. C is minus 100. So you have minus 5 plus or minus over 2a, by the way, 2 times 1. So minus 5 plus or minus 25 plus 100, that's minus 5 plus or minus 425 over 2. So it means that p1 is minus 5 minus square root of 425 over 2. P2 is minus 5 plus square root of 425 over 2. So in this case now, P1, of course, is less than P2 because, of course, in fact, this expression, P1 is negative, clearly, but P2 is positive. So because the coefficient of P squared in P squared plus 5P minus 100 is positive, the parabola opens upward. The parabola has got to open upwards as we have this minus here. So it opens upwards. So we see that P squared plus 5P minus 100 less than or equal to 0 for P falls within the range P1 and P2. However, negative prices are not economically meaningful. So this P that is negative here, it has to go. So we further restrict to P greater than or equal to 0. Thus, the demand feasible price range is actually 0 less than or equal to P less than or equal to P2. Okay, where P2 is minus 5 plus square root of 425 over 2. Like that. Okay, so the interpretation here is that for P less than 0, price is not meaningful, and that is what P1 represents. So that's why we knock it off. Therefore, P greater than P2, which we have here, so DP is less than 0. So the model predicts negative demand, which is not realistic. So if the price is actually greater than this P2, then the model predicts negative. So hence, only what we can have now is that it's either 0 or P2. So this is an economically, and the reason for this is that if we substitute this P2 into the original expression, so if we put P2 into this place, we are possibly going to get something way above 100, and it's something negative, and we don't want that, right? So, but at P2 itself, we are good to go. So this is an economically valid interval for this demand. So anything from 0 to P2 is good pricing. So we can then talk about combining inequalities for demand and profit. So in many realistic scenarios, we require both. So non-negative demand, that's D of P is greater than or equal to 0, like we did before. Then we also want a positive profit, P of P is greater than 0. So solving in each inequality gives a demand feasible interval ID for D of P greater than or equal to 0, and a profit feasible interval IP from P of P greater than 0. So the final feasible price, which is the intersection, I feasible, which is the demand and pricing where they intersect, and price, and so you get the demand at the right price. So interpretation ID, where it makes sense to talk about selling the product, that is demand is not negative. IP, where selling the product actually generates positive profit. I feasible is now where they intersect. So where both conditions hold simultaneously, these are the economically viable prices. So if the point where the selling the product generates profit is equal to intersect with where it makes sense to talk about selling the product, then you have a feasible place to sell. So the geographical interpretation now. On a graph with price P on the horizontal axis, the inequality dP greater than or equal to 0 corresponds to the portion of the demand curve on or above the horizontal axis. So the inequality P of P greater than 0 corresponds to the portion of the profit curve above the horizontal axis. So feasible prices are those values of P where both curves satisfy their respective inequalities. Visually, this is the horizontal region where the demand curve lies on or above the axis and the profit curve lies above the axis. So this graphical and algebraic combination of inequalities gives a powerful way to interpret price intervals and feasibility in economic models based on polynomial functions. So let me see where are the functions now for uh, so we want this to be positive, and if we want this to be positive, this is what it evaluates to. So we have x squared plus 5x minus 100, x squared, x squared plus 5x minus 100, x squared plus what's happening here? X squared, what's happening? X squared plus, okay, we have this. X squared plus 5x minus 100. So, okay, that's too big, so we have to shrink it. So we have this point now. We have this, that's minus 12.8, and we have this. This is not the inadmissible part. This is the admissible part. That's 7 point something. So, and the reason why we rejected it is even if we put 7 here, that's 5 times 7, 35. 7 times 7, 49. 49 plus 35. 49 plus 35 is like, so this is 84. 100 minus 84 still makes sense. Okay, maybe that, maybe if we use the proper thing. So we need positive price, by the way. Right. So we have so this is so in this case now we need a positive thing. We need this particular one now. So it has to be something between 0 and this point because anything here doesn't help at all because we need only positive price because price is on the x-axis, right? So we need like 0, 0 is less than x, all right, is less, I mean, it has to be less than or equal to x, less than or equal to, so that value, uh, that is minus 5 plus root 425. Okay, I can put this in bracket, minus 5 plus square root 425 all over 5, I guess, all over 2, all over 2. So you see, that's what works here. So because the price, which is on the x-axis, cannot be negative, so it has to be between 0 and that's 7.78077. I mean, for you to know that this actually evaluates to that 7 point something something, we can bring this down here and we have it. So you see it's 7.80 blah blah, and that's exactly what this is. So this part is positive, and then we also have positive pricing. So this is the region where the both of them intersect, and that is what we can take in this situation. Okay, so so we have that region like that. All right, so interpreting solution intervals in context. So after solving a polynomial inequality, we usually get a single interval, e.g., closed interval AB or open interval AB. We can also have a union of intervals, e.g., minus infinity to A or union B in comma infinity. Interpretation checklist, you have to talk about the units, attach units like t belongs to the closed interval 2, 5, meaning that time is between is from 2 to 5 seconds. Then you can have closed versus open endpoint, so greater than or equal to or less than or equal to gives closed endpoints, greater than or less than gives open endpoints. You have domain restrictions. Time usually starts at t greater than or equal to 0. Just like here, we have to restrict price to be 0. I mean, so mathematically, we have minus 12 as a possible price, but negative price is not sensible. So we can only do from, in fact, do we even have to include this 0 here? From what we did the other time. Yeah, it's closed interval, I believe. Yeah, it's closed interval. So here now it's closed interval 0 to P2. Okay. So, where are we? Yeah, time is usually t greater than or equal to 0. Length areas population are non-negative. Prices often have realistic bounds, e.g. P is greater than or equal to 0, like we just saw. The reasonableness check. Does it make sense to produce 10,000 items if the model says so? Then you have to, I mean, now that you have got the mathematics, so in the context of your business, you can now begin to think about it if it really makes sense. Then very large or very small values might be outside the valid region of the model, even if they satisfy the inequality. Then verbal summary, you can translate profit is positive for 10 less than or equal to Q less than or equal to 25 into what? That means the company makes profit when it produces at least 10 units, but fewer than 25 units. That's what that means right there. So that's how it can now make business sense to the business owners. So general modeling workflow for polynomial inequalities in applications. So first of all, understand the problem context, identify the key quantity, height, distance, area, profit, demand, etc. Then define variables and parameters. Example, let T be time S, Q be quantity P. Let T be time, in seconds, Q be quantity, P be price. Then build a polynomial model. Like you can use physics formulas, geometric relationships, or economic assumptions. Ensure the expression is clearly written as a polynomial. Then formulate the inequality. Translate phrases like non-negative, at least, at most, profitable, not exceeding capacity. Translate them into mathematics. Solve the polynomial inequality. Find the root first of all. Then use a sign chart or graph to determine where the inequality holds. Then apply domain restrictions like intersection with t greater than or equal to 0 and q greater than or equal to 0, or realistic ranges. Then interpret and communicate in words. State clearly what the intervals mean in the real world setting. If needed, round values appropriately and mention the level of precision. So, yeah, on this note, let's look at the questions. I'm just going to flash them at you. This is about 1 to 3. A rectangular garden has length x plus 3 meters and fixed with 5 meter. We'll write a polynomial for its area. Of course, that will simply be 5 times x plus 3 meter square, right? So use an inequality to find all x values for which the area is non-negative. So that will just be 5 into x plus 3 greater than or equal to 0 because area has to be positive. So that simply means if you divide through by 5, you have x plus 3 greater than or equal to 0. That means that x has got to be greater than or equal to minus 3. Okay? It has to be greater than or equal to minus 3. So if you have minus 3 here, it will be 0. If you have minus 2, it's 1. If it's minus 4, then it goes negative. So that's not working. So the height in meters of a rocket, t seconds after launch, is given by this. So you have this, write the inequality that expresses the rock is above the ground. That means if this is greater than or equal to 0, and then you do all the solution that you need to do. Then 3, a company's revenue and cost in dollars are modeled by this. R of Q, 60Q. So exactly what we did before, you can do the same here. So example 4, the distance in meters between a moving cart and wall is modeled by this. For safety, the cart must stay at least 2 meters away from the wall. So it means D now, this expression has got to be greater than or equal to 2 meter, and collect everything together and solve. Then you have 5, the demand D of P for a product, where P is the price in dollars, is modeled by D of P equals all this. For what price is the model's predicted demand? Non-negative. Okay, so this has to be greater than or equal to 0. Then interpret your solution interval in terms of positive pricing strategies. So we've learned how to do that. A storage tank can safely hold up to 500 cubic meters of water. The volume in cubic meters of water in the tank after 10 hours is modeled by V of T, is this whole thing. Write the inequality that ensures the volume does not exceed the state capacity, greater than or equal to 0, simply. Greater than or equal to 500. I think this, so it can hold up to 500. So this expression has got to be greater than or equal to 500, right? And you do the other maths. Then you have a profit, in dollars as a function. Okay, let me fit 6 to 10 into okay, I think I should do 7. Yeah, this works. So a profit in dollars as a function of price, P in dollars, is modeled by this. Solve P of P greater than 0. So just equate this to greater than or equal to 0. First of all, divide through by 2, before by minus 2. So it can be tidier, easier to handle. And then solve and see what happens. Then the area of a triangle metal plate in square meters depends on the parameter x and is given by this. Find a range of x for which the area is non-negative. So this is a square. Okay, triangular metal plate. Okay, so this is the area. So greater than or equal to 0, and then you see what happens. Explain why negative values of x are not acceptable. Of course, we're talking about length and all that, so that is unacceptable. A machine operates normally only when the temperature T in degrees Celsius satisfies this, where N of T is a normalized performance measure. Solve the inequality for T. Okay, so that's you solving that inequality to make sure this is positive. A factory's weekly cost in hundreds of dollars is this whole thing. And so, okay, with this, we come to the end of this interesting video talking about the application of polynomial inequalities. And that is so interesting because these things have actual applications. Um, I mean, maybe if you're doing a business survey or something, I need some math help. I mean, this can actually be helpful to you, and I'll be very glad to consult for you for sure. Okay, let me know how helpful this is for you, and if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. And if you have not, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also click on join to become a member of this channel. And that gives you some special privileges at the highest level. We can hang out physically if you're in the same geographical space at any point in time, or we can hang out online to discuss anything that interests you on my channel: mathematics, data analysis, data science, SQL, scholarships, machine learning, whatever, we can discuss these things. Okay. All right. Ultimately, don't forget to comment, like, and share so that other people can have access to this great content I have going on here. Till I come your way again, keep doing math right. Bye.